Hi, I'm Brian Sefton, Chief Scientist at Oakbio Incorporated. In this presentation, I'm going to tell you about our CO2s to chemicals production platform. CO2 and greenhouse gases are a global problem. Every year, billions of tons of CO2 and other greenhouse gases are released into the atmosphere as a result of the production and use of petrochemical-derived fuels, plastics, and chemicals. The result of this is greenhouse gas accumulation, global warming, air pollution, and large amounts of chemical waste. Most efforts to address these problems to date have been government-led efforts focusing on subsidizing carbon capture, taxing carbon release, or regulating greenhouse gas production and release. But what if some of those gases could be captured and converted into renewable petrochemical replacement products at a net profit? Oakbio is developing a system to do exactly that. Oakbio was formed in 2008 with a mission to develop a profit-driven biological method for converting CO2 from industry into renewable fuels, plastics, and other chemicals. The Oakbio system is built around specialized microbe strains which absorb CO2 and hydrogen and convert this into bioplastic and biofuels, as well as other chemicals. Our proprietary technology platform can convert waste CO2 and hydrogen into valuable and cost-competitive products at scale. Most people are familiar with how green plants absorb CO2 from the atmosphere and energy from sunlight and use this to grow, and in that way they produce biomass, food, and materials like wood. In the Oakbio process, CO2 from industrial flue gas is fed into the bioreactors along with hydrogen, which can be made from electricity, which is the source of energy, and the microbes convert this to bioplastic, biofuels, and other chemicals. And the advantage of this is the operation can run 24/7, it's water conserving, the microbes are flue gas resistant, and it has a very small land footprint as compared to agricultural methods of carbon capture. The Oakbio system fits in very well with clean energy generation methods like solar, wind, hydroelectric, and geothermal because all of these produce renewable electrical energy. That electrical energy can be used to split water in the process of electrolysis to produce hydrogen, and that's quite an efficient process with modern technology. And that hydrogen can be fed to the bioreactor along with CO2 from industrial flue gas. And I should mention that our microbes are able to grow do not require necessarily clean water, and in fact will grow on chemical waste contaminated water and absorb the chemical waste and convert it along with the other hydrogen and CO2 into bioplastic and biofuels. And those wastes can include acetone, benzene, diesel fuel, dioxin even, and a number of thousands of other compounds. And all of that will be converted into bioplastic and biofuels. The Oakbio microbes are essentially tiny chemical factories. They grow off CO2, hydrogen, and organic acids, and they make up to 90% of their cell weight naturally in PHA, which is an abbreviation of polyhydroxyalkanoate, which is a type of bioplastic polymer, a large family of many different polymers. And you can see in these pictures the microbes have large white circles in them. Those are actually vesicles of bioplastic, showing the large production capability of the microbe. And these microbes are fully sequenced. They can be modified to make new products. We have a toolkit to do that. And they're an excellent platform to make commodity chemicals at scale. Because of our focus in using industrial flue gas as a source of carbon, we decided early on that it was critical to develop our system with real flue gas. And for that reason, back in 2010, we opened a field lab at the Lehigh Southwest Cement Plant in Cupertino, California. The picture on the left shows that. The blue container at the bottom is our field lab, and the pipes connected to it come directly from the flue gas stack. The graph in the center of the picture shows the difference between the original bacteria and how it grew and the flue gas adapted strain that we developed using real flue gas at the Lehigh cement plant. On the far right is a beaker containing white material, which is actual bioplastic that we made from flue gas at the Lehigh cement plant. Now, some people might wonder why we chose the cement industry, and it's a very, very simple set of reasons. The first one is that the cement industry produces about 1.5 billion tons of CO2 a year. Globally, that's 5% of all greenhouse gases, and cement plants are very large point sources of CO2. But another reason is the actual chemistry of cement production, and that's shown here. Calcium carbonate, which is from limestone, is heated, and calcium oxide, which is cement, is produced, and CO2. And so production of CO2 is part of the basic chemical reaction of making cement, and therefore the cement industry, and cement is a critical product around the world, the cement industry will always produce CO2 as a byproduct. But cement plants, as well as CO2, emit carbon monoxide, SOx, NOx, hydrogen sulfide, and other gaseous products or components of the limestone that's mined and heated. They release all these toxic things as well as carbon dioxide. And the takeaway from this is that flue gas has lots of CO2, but also many things which can inhibit or kill non-resistant microbes. To create our N-butanol producing strain, we took these same microbes that produce bioplastic so well, and we redirected the flow of carbon from bioplastic to N-butanol production. And that created this modified strain. N-butanol is a 4-carbon alcohol, which can be both a biofuel and a chemical feedstock. Here's an example of what a partnership with a cement plant might look like. Mid-sized cement plants produce about 1 million tons of CO2 a year. If we caught 25% of that, that would be around 230,000 tons of CO2 a year. From that, would make around 76,000 tons of PHAs or other chemicals. And from that, we would be able to derive around 300 million in annual revenues. That would give us a break-even in 3.5 years, around 3.5 years to break even. For the CO2 producer, they would get either a tax credit or a subsidy, depending on where they're located, which averages around $13 a ton of CO2. They'll be able to increase production, particularly in the United States, where cement plants are limited in their total production by CO2 output, and they could make up to 25% more cement. The cement made when the CO2 is captured is green cement, so they'd get a premium price on that, and that's currently around 175% of what normal cement sells for. They'd also get a little more flexibility in their sourcing of fuel, because when the CO2 and pollutants are captured and absorbed, there's more flexibility in which fuels you use to power the cement plant. So the takeaway from this is that the Oakbio CO2 to product technology generates revenue streams for both the CO2 producer and the Oakbio side, which captures the CO2 and converts it into chemicals. Why N-butanol? Well, that's another pragmatic decision, which is that N-butanol today has a $10 billion market because it's a major chemical feedstock that's used in solvents, paints, coatings, plastics, and a huge number of other products. But N-butanol can also be used as a drop-in biofuel. It's much better than ethanol, has about 86% of the energy of gasoline, which is 30% higher than ethanol. It's not corrosive to engines like ethanol is, and it's a true drop-in fuel. That's a $100 billion market, and our target is to capture 10% of that market for an annual revenue of $10 billion. There's a larger market out there past the horizon of what we want to predict, but N-butanol is a viable alternative to gasoline. N-butanol has a octane rating of 87, and along with isobutanol, these could make a serious impact on the over $3 trillion gasoline market as a replacement fuel. In conclusion, Oakbio has developed a highly disruptive technology which drives carbon capture on a massive scale and its conversion into useful chemicals. Our system is profit-driven and doesn't require government subsidies in order to make money. We use non-food-based feedstocks, so we don't compete with agriculture for land, water, or for the final products agriculture produces. Finally, our products are high performance. They can compete with petrochemical products in both quality and price. Thank you. For more information, go to www.oakbio.com. To find out about investment opportunities in Oakbio, send an email to invest@oakbio.com.